yeah, hi everyone. So what I present today is joint work, with Rico Senklusen and also with Christian Nöbel, who are both at ETH Zurich. And we will talk about two kind of problems which are kind of related, and I will explain you them in the following. And of course, feel free to just interrupt me at any time if something is unclear and so on. And just a very short outline. So for most of the talk, we will actually talk about this graph burning problem, because actually the algorithm that we will discuss works for both of the problems. So this graph burning problem, but also for this clustering problem what we will discuss at the end of the talk. But the techniques are it's a bit less technical to discuss the techniques in this graph burning setting. So here it would be a bit more complicated, although the techniques are essentially use the same high-level ideas, but it's easier to understand in this setting. So what is the problem? So we are given a tree, a rooted tree. So we have some root, which we always depict here at the bottom of our tree, and there some fire breaks out. And at each time step, this fire will spread to the neighbors. So in the first time step to these vertices, then to these, and in the very end, the whole graph would burn down after 3 time steps. And I mean, what is our goal? What do we want to do? So in each time step, we would be allowed to fireproof a certain number of vertices, which are also then in the future, they cannot catch fire anymore. So for example, in the first time step, if we would decide to fireproof this vertex here, then the fire would just spread to these 2 vertices on the left-hand side. And also this would then mean that this whole subtree then is protected from the fire also, like in future iterations. Maybe this already gives a slight idea why this is kind of related to some clustering kind of problem. But this we will come to at the end of the talk. Second time step, we fireproof this one, so the fire just spreads here. And the last time step, we fireproof these 2 vertices, and then the fire cannot spread anymore. And like in the problem that we study, which is like called this resource minimization for fire containment, we would like to protect this given subset of the vertices from the fire. And we can just always assume that these are the leaves of our tree, because otherwise, I mean, if we would require to protect this vertex from the fire, this would also mean like protecting these 3 vertices here, right? So we can just cut them off and consider the sub-instance. Okay. And I mean, here we just discussed it with the fire, but of course this also can be used and is actually studied in all kinds of harmful spreading processes, also like for diseases that spread and stuff like this. Let me also maybe mention that there's also like one other version of this problem where you don't have to protect all the leaves, but just in each time step you are only allowed to fireproof like 1 vertex, and then you want to maximize what you protect, which then is called the firefighter problem. This problem is already well understood in terms of approximability. Peters is known for this problem. So but for this it was a little bit more open what's known. Okay, and here we now have like some strategy, how we protect all the vertices that we want to protect from the fire, but how do we now evaluate the quality of the solution? I mean, in the first and second time step, we just fireproofed 1 vertex, but in the third time step, we fireproofed 2 of them. So the solution actually would then need 2 firefighters to realize this. And this is actually the number that we want to minimize. I would also like to state this problem formally, and for this we will need a little bit of notation. It's hopefully not too much, but let us carefully go through this, because we also need this throughout the talk repeatedly. So I mean, here and also in the following, we will like sort the vertices by the distance to the root. And here's like the distance given, and with capital L, we denote the maximum distance to the root. The leaves, which are the vertices that we want to protect from the fire, we denote by gamma. And now protecting some vertex from the fire can be seen as, like, for each of our leaves, we want to fireproof at least 1 vertex on the wood leaf path. And I mean, we also would like to have like constraints that in each time step we don't want to use too many vertices, right? So how we will do this is like just saying, okay, we denote like the vertices with distance 2, for example, from the root by v2. And then we are only allowed to use this fireproof a certain number of vertices in this subset. Okay. So formally we can now write it down as follows. So we have given a rooted tree, and now we want to find a subset of the vertices, so that first of all, each leaf is protected from the fire, which means on each root leaf path we fireproof one vertex. And second, on each of our levels, we only fireproof B many vertices, and B is the number of firefighters that we want to minimize. Yeah?
I guess just to be clear, you're like assuming, / it's without loss of generality, that like in the ith round of this process, you only fireproof things at the ith level, like you could have your tree.
Exactly. I mean, it's always better, right, to do it like this. So I mean,
do some higher up, but then
exactly. Doing something higher up is not that wouldn't help. Yeah. Then we can just always choose like the one closest to the root, and that potentially protects more. Yeah, very good question. We will also in the following talk a little bit about some LP relaxation, or we will also use it and solve it in our algorithm. So let us shortly introduce this. Essentially, it's like really very straightforward. We just have a variable for each of our vertex. It's 1 if we fireproof it, 0 otherwise. And then we just directly get these constraints that we have a value want to have a value of 1 on each root leaf path, and on each level at most a value of B. And what's known about, I mean, the integrality gap of this LP is known. So it's known to be log star of n, where, I mean, if you don't know this notation, this means how often do we have to iterate the logarithm until we get a number at most 1. So which is actually quite small for, so it's almost constant, but I mean, still super constant. So if we, I mean, what this also means that if we aim for like constant factor approximations, we cannot just solve this LP and use some LP rounding stuff. This wouldn't work. And there are already approximation guarantees which beat this integrality gap. So it started with the 12th approximation by Adyashvili, Baggio, and St-Clusen. And what's kind of interesting is that they still somehow use this LP, which has a super constant integrality gap. And I will describe in a few minutes how exactly one can use this. Essentially, solving this LP can help us to efficiently guess some information about an optimal solution, because the LP has some certain kind of sparsity, and this can help us. But we will discuss this in more detail, because it's also important for us. This also subsequently be improved to a 6 approximation, so Ragushay and Salavatipur, they essentially improved one step of the algorithm where they lost the factor 2, and now they only lose the factor of 1 plus epsilon. Even asymptotically, it's even a little bit better. Then you get a 5 plus epsilon approximation if the number of optimal firefighters is large. And our result for this problem is that we get an asymptotic Peters, so we only lose a factor of 1 plus epsilon, but we also need to round it up. And you essentially have to do this because distinguishing whether 1 or 2 firefighters you need in your solution is NP hard. So the best we can hope for unless P equals NP would be a 2 approximation, which we then now get. And asymptotically, it's even better. I mean, it's still not clear that this is like the end of the story, because what one could still hope for would maybe be like just an additive violation, maybe even just only additive violation of 1. So this is still unclear. In the following, we will,
So just to be clear, I mean, right, for every epsilon, it's every constant epsilon, otherwise I would just take epsilon to be like 1 over n, and I get my additive 1.
For any constant epsilon. Yeah. So it's like in the exponent of the running time. Yeah. Okay. In the following, we will talk about we will just very slightly change the problem formulation, and this has 2 reasons. First of all, it makes things a little bit less technical and will simplify some kind of arguments. And secondly, then we also come around this issue that distinguishing between 1 and 2 firefighters will be NP hard. And for this smooth model that we will define in a minute, we then would get a Peters. And what I mean with the smooth model, so here we have the solution that we have seen at the beginning, where we need like 2 firefighters, which is like in the classical model, then would be like But actually, I mean, it's a little bit better, right? Because in the first and the second time step, we just needed 1 firefighter, and only in the last one, we needed 2 of them. So in our model, it would then be like using 4/3 firefighters, which is like a fractional number, which then means, okay, in every time step, I'm allowed to use 1. In every third time step, I'm allowed to use an additional 1. Okay. And then the problem formulation also just changes just a little bit, which now means that on the first L levels, I'm allowed to use like L times B many firefighters, which now also would make sense for fractional values of B, which wouldn't have made any sense before. Okay, is this like the problem formulation clear? Okay. Yeah.
Wait, sorry. So is it like, are you just saying that on average across all levels you have to use at most whatever your claimed guarantee is, or is it literally like the way that you are supposed to deploy the firefighters is you like?
It's on every prefix. So it's, on average we use 4/3, but you wouldn't be allowed to use like 2 firefighters on the first level and then only 1 on the second and third level. Okay. It's like on every prefix you need to satisfy this bound.
I see.
So with 4/3 you would have a bound of 1 here, 2 here, but on the third level it certainly gets like a 4.
Yeah.
So you can like 2 firefighters on the third level. Okay, now I want to give you an algorithmic overview of the techniques that we use, and I also need to recap quite something that was known in the past, but I think these are like still interesting algorithmic ideas and techniques. And the first thing that we need to discuss is some compression technique, which can be used to reduce the number of levels that we have in our tree. Now looks a little bit complicated. This may be like the most complicated picture, but I just want to give you the very high-level idea because, initially it could be that the number of levels in our tree could be linear in the number of vertices. But this is like bad for even 2 reasons. So first of all, the linear program that we have already seen, it has some certain sparsity, but the sparsity depends on the number of levels that we have. So this would be one reason to reduce the number of levels to get better sparsity. Second reason is that one could also think about like standard dynamic programming algorithms, and the running time would also like kind of depend on the number of levels that we have. So we also for this reason we want to reduce it. And the way how one can do is that one just like certain kinds of levels we keep, other levels we would like to contract. And for example, if we contract now all these levels, we of course then need to add new edges so that the tree is still like essentially the same. So this is like what we would get from contraction. And then this way we can reduce the number of levels in our tree. Of course, if we now have to adapt the budgets that we have, if we assume that initially we were allowed to fireproof 1 vertex on each level, what we now would do is like, okay, here we contracted 4 levels into 1 level, right? So now we would have a budget of 4 on this level here. And of course, fireproofing 4 on this level is a little bit more powerful than like in the original instance, fireproofing 1 vertex on each of these levels, which means that we lose a little bit in the approximation factor with this reduction. Actually, with this, we would lose a factor of 2, but of course, one can also change it a little bit, then one uses a factor of 1 plus epsilon. And now we get these non-uniform budgets. If we do it like this, that like the number of levels that we contract is exponentially increasing, then also these budgets are exponentially increasing, and the number of levels that we end up with would be logarithmic in the number of vertices, or in the original number of levels that we had originally.
So maybe you're about to say this. I'm a little bit unclear on how exactly you're like computing the new budgets, because like just it looks like what you want to do is just sum up the budgets for all the stuff that contracted into the thing below.
Yeah, exactly. This is how it's done. I mean,
Why should I expect that this is like approximation preserving?
I mean, exactly what we do is, I mean, here we contracted like 4 levels into here, right?
Yeah.
But we also have here the property that below of this level, there also already have been 4 levels. So if we assume that initially the budgets are uniform, like 1 on each level, that means that up to this level we already had budget 4. And now I add another budget of 4 on this level, which then would be too approximative, because I just increase the budget up to this level by a factor of 2. And this we can also like push down to 1 plus epsilon, but by just contracting less levels. So then we would require that the budget up to this level should be like much larger than what we contract. This way you can then reduce the loss in the approximation factor. Okay, and this is what we then end up with, especially like if this can be power midwise, as I just said. So we call then instance epsilon compressed if the number of levels is like logarithmic in the number of vertices. And we now have like a non-uniform budget vector which increases exponentially. Yep.
Okay, I think I understand what I was confused about. But
Okay.
So you're saying that when you're talking about the budget, it's like you're talking about the entire prefix budget up to that level. You're not talking about allowing at exactly that level.
Exactly.
Yeah, okay.
Yeah. Which is kind of then also what changes, or what changed when we got to the smooth version, that we always like consider the budget up to some prefix level. Yeah, but this is then essentially a step. I mean, as you already observed, of course, it makes sense to use up the budget as soon as I can, right? But still, it's this like point of view. And also like with the argument that we also just discussed, like on a very high level, one can reduce, like if you have an algorithm for these compressed instances, and maybe let us also assume that for the given budget vector, there exists a feasible solution, which we then call like that it's one feasible, which we essentially can assume because we can just guess like the number of firefighters in an optimal solution. Then we also get an algorithm for a general instance with the same approximation factor, just that we lose this factor of 1 plus epsilon. So,
Okay,
yeah,
so
sure, please, yeah.
There's something that like still confuses me about this, because if I give you like one level and there's like very few things, but not enough to like block all of it, and then at the next, like you're taking these like powers of 2 or something, and compressing it down to that. And between this and the next power of 2, like you have a huge fan out in such a way that like in order to get anything competitive with the original problem, you like really needed to place stuff on these intermediate levels. You can't just wait until the next power of 2 because there's like way too many nodes. Like why doesn't this just like totally kill this compression step? Or, like,
I mean, why this is the case is because, I mean, we are just allowed to do more, right? So, I mean, if you have this problem, I mean, we just push the budget down, right? Which allows us which helps us.
Pushing the budget up.
Okay, exactly. Then you would get into the problem with the very high fan out, exactly. So this is why we need to push it up, which then but means that we lose something in the approximation factor. Okay. We will also now, on the following work with the LP relaxation that we have already seen, just here shown very slightly again, because also this now changes this just a little bit, because now we work with the smooth version. So up to level L, we have the budget of alpha times the total budget up to level L, which is now also like we have these non-uniform budgets, but then this means that we just sum them up to this level. And yeah, okay, it's easily to check that the incidence vector of the optimal solution is indeed in this polytope for alpha equal to 1, because we assume that the instance is 1 feasible. And now I want to talk a little bit more about the integrality gap, because, and maybe also just a short comment, from now on, the instances we work with look a little bit more schematic, because otherwise it would get too complicated. So now from now on, we just have the tree is this triangle, at the bottom the root, and then the trees are just these gray lines here. And I already told you that integrality gap is like log star. actually not log star of n, but log star in the number of levels that we have in our tree. But what's interesting is that if we would have a fractional solution which has no support on the very bottom levels, then this integrality gap would become constant. And this would improve if we go higher up in the tree. So if here, all on this part up to level log L, we don't have any support, then we have an integrality gap of roughly 1. And then we could just, if we would have such an LP solution, we could just do normal LP rounding stuff, and that's it. And maybe just a very high level idea why this is the case. I already told you that like that the sparsity that we have, this depends on the number of levels, right? And the sparsity, what this exactly gives us, is that we don't have too many fractional vertices in an optimum vertex solution. And what we then can just do, okay, just pick every fractional vertex. Then you of course make an error, but if we're already up to this level, then we know, the budgets, they increase exponentially. So this then means that already on this level, we have enough budget that even if we pick like all these fractional vertices, this is only an epsilon fraction of the total budget that we already have here. So this is why this would help us. Okay. Of course, this doesn't have to be the case, and especially an optimal solution could look like this. So we have like this threshold height h, which we would like to choose like as before as log L, so that we have this small integrality gap at the top. So this is just we denote by h in the following. And here you can see an optimal solution, which are the blue squares that you can see here. The leaves are the cycles at the top, and the red part is the part of the tree that burns down during the process. And okay, let us for now assume the following. We partition the leaves into two sets. The right-hand side are those which are protected by op vertices on these top levels here. On the left-hand side, these are the leaves which are protected by top vertices, by op vertices on the bottom levels. If we assume we would know this partition, then I would say we are more or less done. Because on the right-hand side, we could just solve the instance restricted to the top levels. For this, we have a small integrality gap, so there we can use LP rounding. And on the left-hand side, we can solve the problem by just using a simple dynamic program. Because, I don't have time to go into too much detail here, but essentially, in the dynamic program, you have to store all the states that you have, and you have one state for each budget vector that you used for your partial solution somehow. And if the total budget is small, then you can do this efficiently. And we know the budgets increase exponentially, so if we have a certain threshold height, like the log L actually would be enough so that we can do this efficiently here. So maybe not too, if you, maybe can you look into the paper on how exactly this dynamic program works. This was also already known before, but for us it's maybe also only important that if we only have an instance with not too much budget, then we can solve the problem exactly using dynamic programming.
Okay, so something, I know this is all just intuition, but something that's a little bit confusing to me is I'm imagining that the threshold is something like the last 1 plus epsilon of the tree. And so it seems like low budget, if the protecting is happening right before this threshold, low budget is you're within the 1 plus epsilon of your entire budget. And then I don't understand why that's sort of so much easier than having the full budget.
You need to have a huge difference between the budget that you have up to here and compared to the total budget, right? Yeah. Do I have it here? Oh, no. But the budget is essentially something 1 plus epsilon to the level that you have. Mm-hmm. And if the level is logarithmic in the number of total levels that you have, and okay, maybe for this makes sense to shortly write it down. Or should I just here? Or?
The camera will
the camera.
If you do that.
Okay. So the budget up to level h is 1 plus epsilon to the h. So that we have like these increasing budgets, which are just like the outcome of the compression that we used. And now, if we choose our threshold height to be logarithmic in the number of levels of our compressed tree, this is like L. Or actually, like, I mean, this is like the logarithm to 1 plus epsilon. And L, I mean, due to our compression, this was already like logarithmic in the number of vertices that we have. So the total budget is just logarithmic. And this is why then the dynamic programming works, because then this allows us to just store all the different states that we have. Okay, does this make sense high level? Okay. Okay, this is essentially what I've already said. So if we would know this partition, so which vertices are protected by the bottom levels and which are by the opt levels, then we would be done. Of course, computing this partition is pretty much unclear how to do this. And we won't do it exactly, but yeah, I will explain in the following how we can do this. And for this, what we will do is that we use some enumeration algorithm where we let us guide by fractional solutions. And yeah, I will tell you this in the following. And for this, the following observation is important to do this kind of efficiently. So let us consider some support vertex and just some fractional solution. And what we would like to guess in our enumeration approach is how the leaves are protected by the optimum solution. And essentially, there are different kinds of situations that can occur. So first of all, we have the one here on the left-hand side, where we see that all the leaves in the subtree rooted at this vertex, they all are protected by this vertex, op vertex here on the bottom levels. So this is like bottom protected. On the right-hand side, we have this support vertex here, and here we see all the vertices in the subtree are protected by the vertices on the top levels. This we then call top protected. And these are kind of nice because it's just a yes-no decision that we then have to make, and this can be enumerated quite efficiently. But of course, it could also be that it's a mixture of both. So for this vertex here, for example, we have like these vertices in the subtree which are protected by this one on the bottom levels, but also here like other ones which are protected by vertices on the top levels. But the nice thing is, okay, when does it can occur? And actually, we can really pretty much just describe the vertex set for which this is the case, and this doesn't contain too many vertices actually, because these are just exactly the vertices which rely on like paths going from the root to opt vertices in the bottom levels. So like, for example, all the vertices on this wedge path here. And these are not too many because, I mean, the total, I mean, how many opt vertices do we have here? This is just what we have seen on the whiteboard recently. It's 1 plus epsilon to the h. It's just the total budget that we have. And of course, each of these paths can have a length of at most h. And for the right number of h, this is small enough do the following idea. Because what we would like to do is that we now iteratively solve the LP until this nasty case here doesn't occur anymore. Because for this, we cannot just make a yes-no decision. This is kind of bad for us. So we do the following. Again, here optimum solution that we have seen before. And now we just solve the LP. Maybe we get this solution here. And now we see, like, in the red part is like this core set that I've described before, for which it's not that easy to make this yes-no decision. And here we have like these two vertices, which are like in the core set. And what we now just do in this first version is just very, very, very simple. We just guess all the vertices which are in the core, and for those we had to constrain to our LP that they should be 0. And then we resolve. Then we get like this solution. Again, here we have like two vertices which are in the core set. Also for those who would have the constraint that they should be 0. And this we just iterate until eventually we end up with a solution where the intersection with the core is empty. Now it's pretty nice because now for all the remaining support vertices, we can just do this guessing, like are all the leaves in the subtree protected by bottom levels or by top levels. And just a short comment, for a certain height of h, already this very naive approach is already efficient. It's maybe not too important to pass this like in all the detail, but like this approach that I just told you would be sufficient so that we have an integrality gap of roughly 2 on the top levels. To get a Peters, we need an integrality gap of roughly 1, so then one needs to refine this approach, but I won't go into that during this talk, but this is like one of the barriers that we like need to overcome to get the Peters in the end.
Oh, yeah, maybe I just missed the definition, but it seemed like deciding whether or not a vertex is in the core requires knowing the optimal solution. And so when you're updating, like what are you actually doing when you're updating?
We enumerate. It's very naive. We just enumerate all possible, like all the subsets.
Oh, I see.
And the total support is small because of our sparsity guarantees, and that we have small budget on the bottom levels. But this is like the most naive thing that you can do. But this already allows us to go up to this threshold height. If you want to put it or higher so that you have small integrality gap, then you need to do something more involved. But this is like already enough for this. I mean, then we just do what I said before. So for each of the support vertices, we guess whether the vertices in the subtree are protected by some op vertex on the bottom levels, which would be the case here. So this will be part of our bot partition for bot set for this one in the top set. There are also some remaining for which we don't have any support vertex on the path up to the threshold height. Those we would also put into the top instance. Why do we do this? Assuming that all of our guesses are correct, okay, maybe first of all the observation that we already had, like for the bottom partition, like the optimal solution restricted on the bottom levels covers all of it, and we can find the solution or a similar good solution via dynamic programming. And for the remaining vertices, we can find a good fractional solution because like which just has support like on the top levels, because we just take the incidence vector of the opt vertices on the top levels and our fractional solution on the top levels. And this covers like the gray vertices then and the red vertices. But we need like to sum like these both, which is then a fractional roughly 2 feasible solution. And this just summarizes it. So, but what does it mean? So on the top instance, we have a fractional 2 feasible solution, and we have an integrality gap of 2. So there twice we lose a factor of 2, which then would give us roughly a 4 approximation for smooth RMFC. This is already a little bit better than prior work, but it's kind of like streamlining and smoothing the analysis and where they lose a little bit. And but yeah, this is or essentially what was like already known. But the main obstacles now to improve it, like okay, we just have lost a factor of 2 in the construction of the fractional solution. Then we only have an integrality gap of roughly 2. And to overcome this, I won't go into detail here, but just a very high-level idea is that we don't just stop the process until we hit the first fractional solution which has non-empty intersection with the core set, but we just iterate. In the end, we take the mixture of a certain number of a linear number of LP solutions, and for this solution, one can show that this is then almost 1 feasible for the top instance that we construct. And the second thing that we need to do is that we need to increase the threshold height so that we only have, or that we have an integrality gap of roughly 1 on the top levels. And we do this by thinning out the core. So again, here in this example, the core set would be like for this threshold height, these blue edges here. For this one would be these blue edges. In the end, the core set, the thin core that we construct is not even anymore like connected. It has like different components. But actually, we can say that if we have some solution which has non-empty intersection with these edges here, with these blue edges, this would already be fine enough to construct a good solution on the bottom levels. It's not anymore 1 feasible, but it's like 1 plus epsilon feasible. Okay. That's it for the firefighting problem. And now I would like to tell you how this translates to non-uniform K-center and what are the results that we get for this. So in non-uniform K-center, I guess probably most of you know the K-center problem, where we like want to cover like vertices with K balls, and we want to minimize the size of these balls. And now in non-uniform K-center, we have like given or pre-described radii, and together with multiplicities, we still want to cover all the vertices, and we want to minimize the factor by which we multiply each of these radii to cover the whole metric space. Maybe it's easier to just look at this example. So we have 3 different radii, so the large one, the medium-sized one, and the small one. This does not yet cover the full all of our vertices. But if we would increase each of them by a factor of 2, then we would cover everything. So this would then be a 2 approximate solution. So this is a factor that we want to minimize. By how much do we need to enlarge these balls? Okay. And unluckily, computing a constant factor approximation is NP hard. So we cannot hope for getting a constant factor, which is why people also turn to studying bi-criteria algorithms for this problem, where we do not only allow to enlarge the balls, but additionally we are allowed to open more balls. So for example, and this is then the factor alpha, so we are allowed to open like alpha times the initial number of balls of each size. And then for this problem, there is a bi-criteria approximation algorithm that's known, which gets a constant factor in both. The number of balls and the sizes of these balls. And maybe let me also mention that, okay, this is still NP hard for some alpha being smaller than 2, and actually this hardness also comes like from the resource minimization for fire containment, so for the problem that we studied before, and for any reasonable choice of beta actually. And what we get is that we essentially get like this 2 factor in the balls that we have to open, and I would say actually we tried put quite some work and also keeping the second factor small. So there we now get like a 15 approximation roughly. But our result is even stronger in the following sense. So for example, for MFC, we have like considered the smooth variant, right? And how does this now translate to non-uniform K-center? What we actually can do or can guarantee is that for the L largest radii, we only open, and this holds for any L, we only open like 1 plus epsilon times this many balls. Yeah.
Could you show me the hardness of approximation again? That's about
yeah.
What exactly was it?
Yeah. So essentially, you can just.
The number of balls is supposed to be within a factor of 2, so it's.
Yeah. Exactly, but this is like means okay. I mean the issue is here that, for example, the multiplicity could always be 1 of each ball, and then needs to be 1 ball that you need to use twice, right? Or this is like the hardness. There's 1 ball which you need to use twice, and then you directly lose a factor 2 here. But essentially, I mean, and this is like what I would like to say with this is, I guess in many applications, this is not what we are interested in. We are interested in to minimize the total increase in the balls that we use, and maybe also reflecting that balls of larger radius are more valuable, which is then like this guarantee what we get here, and then you only need to open like 1 plus epsilon many times, or lose only this factor on the number of balls that you open. Maybe one interesting open question is, so this hardness result only applies if we have an arbitrary number of different radii, if this number would be constant, then it's conjectured, then we could then get a constant factor approximation, even if we don't open any more balls. For up to 4 different radii, this is known, but already with 5 different radii, this is still an open question. And yeah, so this is just the final slide where it just summarizes like the results that we have seen before. And yeah, thanks a lot for your attention.